Okay.
So this is sort of an experience report for Google Summer of Code 2010 for the project that I mentored, which was on Voronoi diagram of line segments. I'm Luke Simonson, I'm the Boost Polygon author, and my student was Sydorchuk. So first I'm going to give the problem statement for the Voronoi computational geometry problem that we solved, the motivation why you want to solve this problem, and sort of the timeline and history of the project, how it unfolded, then an explanation of the actual algorithm we implemented to solve it, or actually the student. I didn't write a single line of code, which is kind of like the Tao of programming, code without coding. But, and then the numerical robustness problems that are inherent to the problem that we solved for making it actually correct. And then show you some nice output examples and benchmark results, and the plans for the future, how I'll integrate it into Polygon, and how the 2011 Google Summer of Code project will tie in. So the problem, we'll simplify it to the special case of Voronoi diagram of points, is given an input set of points called sites. We want to compute bounded regions called cells for each site such that the site enclosed by each cell is closest to all points in the cell. So the cell, basically everything inside the cell is closest to that site versus any other in the set. The boundaries between cells are Voronoi edges. The intersection between three or more Voronoi edges is a Voronoi vertex. So there's a related problem, the Delaunay triangulation of points, where here, this is a Voronoi diagram, and these other edges are the Delaunay triangulation. Basically, it's the dual graph of the Voronoi diagram, and so if you solve one, you solve the other, and there's no reason to implement both. It just is a graph transformation. And actually, the output contains both graphs. So the Voronoi diagram of line segments extends sites to include segments. So then the Voronoi edges may be a parabolic arc where you're equidistant from a point in a segment. And we usually model the endpoints separately. So this is equidistant from the point in this segment. That's where those edges come in. And another related problem is the medial axis of a polygon, distinct from straight skeleton, which is actually unrelated. The medial axis of the polygon is essentially just the Voronoi diagram of the line segments of the polygon restricted to the interior of the polygon. And nearest neighbor query, if you have a bunch of points and you want to know who's the nearest neighbor of any point, you can get it directly from the Voronoi diagram graph. And you can do all kinds of things with segment-based, where you can find which polygons are enclosing other polygons by traversing the whole graph, and which polygons contain points versus not, these types of things. And you'll notice, optimally, 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 optimally. If you do all of this stuff with a query tree, then you have to prefix sub on all of those optimallys. Anyways. So it's one algorithm to rule them all. We've got all of these problems we can solve with a single implementation of an algorithm. So there's a strong motivation to implement this algorithm because it gives us so many useful things. So the algorithm we chose to implement is Fortune's algorithm. It's the sweep line, the first algorithm, I think, for Voronoi. And he explains how to do it for points, and then says it's easy to extend this to line segments. And then nobody could publish the version that actually does it on line segments, because they're like, well, we knew that. Fortune said it was obvious. But there's a lot of details in there that you have to rediscover that was more than he could put in the paper, which is why you do it that way when you write a paper. So,
job security.
Of course, we want to solve all these problems because there's lots of applications for them in, physics and data compression, and my field of CAD, CAM, uses a lot. The medial axis is important. in geospatial information systems. I suppose the boost geometry guys will be interested too. And meshing, the Delaunay triangulation is very important for meshing because it gives you a high quality mesh, where basically very acute angles have bad quality in a mesh because you have poor numerical stability. The Delaunay triangulation sort of minimizes that. So for the history of the project, I proposed the idea in March, and then we had several strong proposals come in from students in April, and I selected Andre. He wanted to solve the problem whether he got paid or not, which is great because once Google stopped paying him, he kept solving it. So that's why that doesn't end at the end of the summer, right? So we started work in May, doing lots of research, reading papers. I was reading papers, trying to figure out how to do this anyway. And you know, in June he got Voronoi points working, and then in July he extended it to segments, threw away the points implementation because it covers both. And July and August and September, and work has been ongoing basically all the way up to, you know, the past couple of weeks. So improvements go in. It's not really the sort of thing that you can just say, oh, there, I'm done. There's endless bits in the bottom to keep pushing precision. About 4,600 lines of code, so we're getting about $1 a line of code for Google's money, which is pretty good. It's well below the industry standard, I think. And given what he's done, I'm very impressed with this student. What he's done has a commercial value of at least $50,000 to pay a contractor to do it, and probably more. And you know, the value of it may be more in the $500,000 or higher range. So the ROI for Google's money is great, except it's free, so nobody's actually going to charge for this. But the benefit should be great to companies in terms of cost saving. At least they save a CGA license potentially. So Fortune's algorithm describes a sweep line algorithm for Voronoi of points. It's similar but more complicated than the Bentley-Oatman type sweep line for line segment intersection. So, and as I mentioned, he gives the general idea for extending it to line segments. Has the same n log n complexity of the classic sweep line algorithms. And there's also a divide and conquer and randomized incremental construction algorithm for solving a Voronoi diagram of points or line segments that have the same n log n complexity, but they're not really simpler to implement, and Sydorchuk's claims aside, I don't believe they're faster. Jonathan Sydorchuk implemented all three for points and then did a performance comparison with the claim that he did his best for each of them, so we should believe him which one is faster. Anyways, so the algorithm is you start with a sweep line, vertical sweep line at the left, and you sweep until you reach a site. And the sites are where work is done by the sweep line. After the site, you open up a parabolic arc. Conceptually, we don't necessarily model it that way, where the parabolic arc is equidistant from the site and the present location of the sweep line, and we keep doing that as we reach sites. And those arcs widen out and merge, and where they merge, they start forming Voronoi edges. And you can see as these will sweep forward, it's describing the Voronoi edge with the forward progress of the algorithm. It makes a neat little movie. When three parabolic arcs come together, that creates a Voronoi vertex. And that's where we have work to be done in the sweep line to do our bookkeeping. We proceed until we've hit all sites. When both edges, when you complete a Voronoi vertex, you write it out to the output data structure, the edge related to it. So our sweep line is just a standard map where we actually store the intersection between parabolic arcs is the element of the map. And the output data structure is what's called a quad edge, where an edge of Voronoi vertex and a site are all nodes in a graph, and each edge is a quad edge because it has 4 pointers or 4 edges in the graph. It's confusing because we have too many kinds of edges in our terminology. And this graph then that's built out of all of those is the output data structure, and it has both the Voronoi cells and the Delaunay triangulation represented in the graph just by walking it. So once there's no more sites, the algorithm is complete, and any incompleted edge, Voronoi edge, just goes out to infinity at that point. And the typical thing you would do is clip it so that you don't have infinities running around in your program. So going into a little bit more detail on the circle events, which are the places where Voronoi vertices are formed. These are circles where there's 3 or more input sites equidistant from the center of the circle. What you do is you take 3 sites and you inscribe a circle on them. And the event point for the circle event is the rightmost part of the circle. When we reach that point, and we can go there now, when we reach that point, the center of the circle is equidistant from the sweep line and the 3 points. And that's where a lot of the work of the algorithm happens, because we have to merge these 2 elements in the map that's representing the sweep line. And now put our Voronoi edges that we've completed at that point. So in Fortune's algorithm, the order of the circle events is maintained in a priority queue, because they're being generated and consumed, as well as invalidated sometimes by the forward progress of the algorithm. And it's not really a fatal error if you get the order wrong. You just get the wrong topology of your output graph. But the algorithm continues on perfectly happily, it doesn't crash, you don't get undefined behavior. The order of the parabolic arcs in the sweep line, maintained by a map, that needs to be exactly correct when you compare them, otherwise you violate the invariant of this container, and you get undefined behavior. So Fortune's algorithm for segments works the same way. Each endpoint of the segment as well as the body of the segment is modeled as sites. And in our case, we actually model each side of the body of the segment as separate sites because it kind of makes it easier. You're all points equidistant from one side, and then the other side is a different cell, basically. It just makes it easier to think about as you're programming it. And then to compute your beachline events, you have to find the circle inscribed by all of these combinations of point and segment sites, which require a different complicated equation to solve for it in each case. And those contain square roots, of course, in all cases, which makes it numerically very difficult to come up with an algorithm that's actually going to work correctly. So, for achieving numerical robustness in our implementation, we assume integer input coordinates and output coordinates. So when it comes to computational geometry and numerical robustness in general, in order to achieve, well, you have to assume some output representation that isn't real numbers. So whatever you do has to end up there eventually, which means there's going to be an approximation made at some point. Now, to achieve efficiency, you need to find somewhere in your algorithm to make an approximation. And the key thing is that that needs to be safe. It needs to be safe. Your algorithm will still work correctly. It won't crash due to the approximation. And it also has to be reasonable, which means your output has to be still meeting the requirements of whoever is going to consume it. So a good example of that, the Voronoi diagram should describe a planar graph. If you try to do 4-color graph coloring on the output, but it doesn't happen to be planar, the algorithm will never terminate. So that's a fatal error for us. So we will, because there's square roots in the computation of the circle event, the Voronoi vertices can't be represented exactly in any way. And so we want to bound the error on those basically to below integer rounding error, since that's what we're snapping to in the end anyway. But we need to do better than that in order to get the topology correct, because ideally we want the exact topology. Anything else, and people can detect that and will call the algorithm incorrect. We also want the algorithm to be fast with minimal use of infinite precision arithmetic. Just saying I'm going to use infinite precision arithmetic everywhere is a cop-out. That's not a solution for anything that's practical. And in our case, it's not even possible because an infinite square root is infinitely large and not useful. So we need a reliable way to deal with the irrational value of square roots in the algorithm. So embarking on this long journey and achieving all of our goals, we need to handle the fact that floating point is an approximation, understand what that means, and how we can make use of it. So here I have some expressions for estimating the relative error of basically any calculation here. It applies to floating point, but you could do the same thing with a slide rule. And the key thing to notice here, if these all had the same sign, it's subtraction that's the problem, because you get catastrophic cancellation. And the size of your error depends on the actual values of the inputs. So it can be arbitrarily large, and of course the closer together they are, the larger it is. So then how we use that, you end up, you can think of your relative error as providing an interval of uncertainty around the answer you got. And if those two intervals overlap between two numbers you're going to compare, then you can't trust the result of that comparison. So in floating point we have machine epsilon, which is basically your floating point rounding error. And then we also have what's called units in last place, which is the smallest representable unit in your floating point representation. And because units in last place is always at least big or bigger than your machine epsilon, we can use it as a proxy for the machine epsilon in estimating our relative error, because what we really want is a reasonably tight error bound. It doesn't have to be exact, and your algorithm is still correct. So to compute the units in last place for error of floating point operations, you just use the equations on the previous slide and add 1 to all of them, because each operation in general is going to add one unit of imprecision. And then those accumulate as you go through more operations.
Those are absolute errors, not relative errors.
Units in last place?
Yeah.
It is relative to your exponent still.
Yeah.
We like to think of it as an integer. It's like it basically tells you how many bits you have that are bad. That's how I like to think about it. So my student implemented this nice relative error accumulating floating point type, where he's adding basically one ULP and doing the expression for multiplication to compute the relative error as well as the floating point result. And because they're both encapsulated in the same type, you can have stuff that looks like regular floating point arithmetic but is propagating the error through it, which makes it much easier. You don't have to do it on paper. Yes?
So there's the interval arithmetic library.
Yes.
Okay.
The boost interval can be used to compute tighter bounds on relative error than what we're doing, because it uses the actual rounding modes of the floating point unit to round up and down when you do the arithmetic. If you have two values u and b you're going to add, you make them, closed intervals, add them with the rounding, and this gives you your interval of relative error. It's very slick. It's a hard library to implement because you have to fiddle with the rounding modes and all of the different architectures. Another thing I'll note, the documentation of boost interval doesn't describe this motivating use case that I could find, but I kind of knew that's what it was for. The student actually didn't use he doesn't depend on anything but the STL. He doesn't even use my stuff, so as much as I encourage him to. And I suppose I sort of have the same fault, right? Famously. Yeah, so the result of doing the boost interval thing is a nice tight bound on relative error. If u plus v is exactly representable, then it stays a tight bound. It doesn't increase by 1 ULP for no reason the way ours does. And so we're going to explore applying boost interval in our implementation. So once you know, using the floating point accumulation of relative error by whatever means, that you don't trust the result, you can fall back on infinite precision. Infinite precision arithmetic is very expensive, but if you have good bounds on error, then it should be very rare that you actually have to use it. And then the result is an algorithm that runs almost as fast as if you didn't use the infinite precision, but it's actually correct. And this is called lazy exact arithmetic, and it's commonly employed all over the place, and especially in computational geometry to deal with numerical robustness problems. And you think, okay, now we're done, right? We're done, we know how to... No. Okay, we'll get to it, but that's just still only the start. So to integrate GMP, which is the library for infinite precision arithmetic, we can't depend on it directly because it's not Boost licensed. So we're going to use the same mechanism as the Polygon library to make it something that you can specialize and tack on without having a tight coupling to it. And this will allow other data types to be swapped in if you choose. Which is actually handy because I'll show you later we have some ideas for improving on it. There's this performance problem with GMP. It has a nice C++ wrapper that turns it into a regular numerical data type, and it even has expression templates to deal with some of the copy. And now we have move and everything should be wonderful, but it turns out eliminating the copy almost gives you nothing because GMP runtime can be dominated by your allocation and deallocation time. The guys who implemented GMP basically do hand-tuned assembly for all the important algorithms on all the important architectures, and even some unimportant architectures. And so the algorithm runs fast, but if you're generating a temporary, going and allocating, and especially deallocating that guy, is where your runtime ends up going. So optimizing your usage of GMP really involves optimizing your allocations. What you want once your algorithm hits its stride, you should never be allocating, at least for GMP, anymore. Of course, the map will be using its allocator. So you can avoid temporaries, of course, by just writing one arithmetic operation per line. That's not very satisfying, not very readable. Not that the code is that very readable anyway, but we'd like to do better. So the student went ahead and implemented this wrapper for GMP, where he basically keeps a circular buffer of temporaries in a static array, and then every time he needs to return a temporary, he returns a reference to one of these. And I hate this solution because it's not thread safe, and I'm wondering how can we solve this problem better? Does the audience have any ideas? There's a problem with many expression template systems. I would expect at least somebody would say thread pool or use a pool. Yeah, it's a crummy pool. Use a thread safe pool. Yeah. We could make it thread safe, right? Maybe a lock free pool. Anyways.
No, you forgot use locks.
Oh.
Yeah, use locks would be your first.
I think I didn't even go to the first step. I forgot what it was. Just don't write parallel code.
Right.
Yeah, somebody else is going to write the parallel code, and then we want it to work. So my idea was to store a temporary 1 in each of the wrapper, where the temporary returns a reference to himself with everything that would have returned a temporary. Because if you think about it, the temporary is an R value. The R value is movable. It can only be used once, so he can modify himself. And he has to have a mutable number because everything is going to be const ref that it's working with. And this way, if I cache all of these guys in the Voronoi algorithm object, and I'm reusing them, I'm also reusing their temporary buddies as the result of any of the expressions. And I can't really think of anything that's wrong with this, except that it's kind of ugly.
Well, so going back to the fundamental problem, is there really a reason for this to be thread safe? I mean,
Yeah. If it's not thread safe, then that's a bad feature of it.
well, I'm just saying that when you're running the algorithm, are you spawning multiple threads?
No, I'm not. It's the client code may want to thread it.
It's their problem to keep
Yeah.
their application thread safe. It's
Yes,
outside
but if
of
I
your
use
system.
static, they can't fix it in the library.
Yeah, he's hiding that he's got.
Oh, is there statics in there? Yeah.
Yes.
Okay.
Is this
Well,
guy.
sure,
They can't
but
really fix that.
One,
They put a big locker on you. Is that something?
Yeah,
just-
that's
It
what they
did
do.
not allow any Voronoi algorithm to run in parallel. They're probably not happy with that. One thing you might want to do is I have this
Okay.
clever idea for a divide and conquer Voronoi where I'm going to run the sweep line in each thing and then merge them, and it doesn't work.
I mean, you could just carry around an object of caches which is stack, it's local, thread local.
Yeah, I was telling him to use a pointer here, but the problem is these guys have to have the same constructor as any other numerical type because it's in a templated context that they're used.
You could just pass an extra parameter everywhere which contains this, it's ugly.
What do I do if they use long double instead of my type? It's used in a templated context, so it either has to be global data or member actual data. I think this will work. This is.
And making everything move aware doesn't get rid of all your temporary problems?
It doesn't get rid of the allocation, right? And the allocation is a lot more expensive than the move, and than the copy that the move takes care of. And the copy is way faster than the arithmetic was. So we're solving a problem, but it's not the big problem that we have for performance release with the move aware. If there was no heap allocation, then move would be fine. So, as I was mentioning, we're not done just because we know how to do lazy exact and computer error bounds because of square roots. So if we want to compute a minus square root of b, and a is greater than 0 and almost equal to square root of b, then the error will be huge. And we can't just say, oh, the error is too big, we'll recompute it with infinite precision. I mean, there is infinite precision square root. You can keep expanding it to larger and larger, but it gets pretty complicated. And you don't really know when you're done. At what point do you say, okay, they really are equal? Because you can just keep expanding. In this case, it's a, but if there was square roots on the other side. So we need to avoid catastrophic cancellation error while still using floating point square root effectively. And of course, in these complicated, segment point, segment type, circle inscribed equations, we can have many, or more than one square root, up to 4 actually. So what the student came up with, and I think there's a paper that describes this, is refactoring by conjugates to eliminate catastrophic cancellation, where you can check the signs of things and then have alternate equivalent expressions, where you might have actually many more operations, but much lower relative error when you do this algebraic transformation on the expression.
Can you not just use the series expansion on the square root?
Yeah, you can. Of course, you can keep expanding it. It's much nicer to not have to do that at all, though.
No, but I mean, you want to do the series expansion, and then you take the constant with the first few terms, add those together, and then expand the rest. And that way you can reduce your error, because if they're very, very close, then
Yeah, you can just keep expanding until you're confident in your result. That's the normal way to do it.
No, but I mean, you want to expand the whole expansion.
No, not the whole expression, just the square root part, yes.
But I think if you
Not the whole. No, not there is no whole expansion, obviously.
but if you put in the a into what you're expanding, then
Oh.
it should be better, right?
I see. And perhaps we can talk about it offline. I'm interested in alternative ways to do it. We've been exploring many different alternatives actually with the student doing research and trying things. So by doing this refactoring by conjugates, we can cover all cases of positive and negative factors of square roots up to 4 square root terms in an expression that looks basically like this, without cancellation error if you have enough conditionals in there. 5 or more can't be handled. We're lucky that we only have up to 4 in our equations, and we'd be luckier not to have square roots at all. Then it would be an easy problem like I was dealing with for the polygon clipping algorithm I implemented. So for the points case, we use lazy exact for the sweep line predicate, where we don't even use GMP, we just emulate 65-bit integer arithmetic, because that's all we need to get an exact result, given input integer coordinates. And for the circle event in the Voronoi points case, we use lazy exact to within a small bounded relative error. So first we do floating point calculation, where we're careful to avoid cancellation error as much as possible to get a minimal error, and then check, see if it's below our threshold, and if it's not, go ahead and recompute with infinite precision except for the square roots. And so we use the wrapped GMP numerical data type I showed before when implementing that. And here's what it looks like just for the approximation portion of the code, where here is falling back on infinite precision, and he's using his robust floating point type, which is just accumulating error. And this epsilon robust comparator thing is actually, it's a numerical data type where if you have a difference in sign in an addition or a subtraction of the same sign, it actually stores 2 floating point values, and it defers your cancellation until the last step, where he calls diff. And so you minimize the cancellation to 1 operation, as well as, because he's using his robust floating point type in it, he knows what the error was. And here he's checking with his threshold of 128. I asked him, how'd you choose that threshold? And he said, well, if it's too big, then it might not work correctly, and if it's too small, it will be slower, and we don't really know what the perfect value is. I'm probably not happy with that answer, but it's, as I say here, it's hard to prove what the right number is. So for doing the circle events, we're actually computing the value for the circle and then comparing those values in the priority queue. And because there is error in the values, the order can get out of whack, potentially, which would result in the wrong topology. So it's correct to within a bounded relative error, which is distinctly different to correct within some epsilon that you choose with epsilon rounding, which is not a suitable way to solve the problem. So in the previous slide, we have 128 ULP as his threshold. So that's 7 bits in the bottom of the double, which is 2 to the negative 45 integer scale. And since we have integer input coordinates, we're mostly happy with that level of precision. I'd rather use long double rather than double, and we'll have a type trait eventually in the coordinate type for what approximation data type you want to use. And so with long double, our relative error would be less than the machine epsilon on double for the exact same code. You just change out double from long double. And that's the exact answer according to people who don't think about what goes past the end of their last bit in floating point very much. And as I mentioned, it may be provable that with a sufficient error bound, you cannot get an incorrect topology in the output of the algorithm using the knowledge that the input coordinate data type is integer. And it may also be possible to prove that for a given floating point input coordinate, sufficiently low error bound, obviously below the bottom of that floating point, possibly much below it, would be sufficient. We have various papers written that say you need, 12K bits or something for various things, and then of course if they're exactly equal, you have to expand all the way out. We'll come more into degeneracies later. So the predicates for segments, because we were just talking about points, the predicates for segments are basically the same, but a little bit more involved, and the circle event ones especially. So what we're doing currently is we're using infinite precision all the time for the segments, and floating point just for the square roots, refactoring by conjugates as I showed you, and using infinite precision for the regular arithmetic so that we get basically zero relative error there and minimize the relative error due to the square roots, which gives us a very small error bound. We've implemented the floating point approximation, but it's not currently used because we're trying to get the algorithm correct, and then we'll swap it and make it faster. So, some examples of the output. So, this is several line segments where we computed the Voronoi diagram. And let's see if I can turn off the front lights so it's a little easier to see. This here is the degeneracy, where the distance between the end of this line segment and this line segment can be arbitrarily small. You could probably prove what the minimum distance is using the fact that the input coordinates are integer, which goes into how we prove how much precision is really required to be safe. But we can see, at least in this case, it's handling it well. And this is one of the types of things that we need to be concerned about in the algorithm in terms of difficult inputs. And this is just a normal case, easy to handle. And you see the sweeping parabolic arcs of the Voronoi edges in here. Here's another degeneracy. This is a circle of points that are very close together. They seem to almost be overlapping because of the size that they're drawn at. And if they were perfectly circular, there would be just one Voronoi vertex in the center and radiating outward all of the edges. Because they're on an integer grid, they're not quite perfectly co-circular, and you get all of this mess in here of different Voronoi vertices at different distances. And the co-circular points are the worst case for Voronoi diagram algorithm. And especially in CAD, every rectangle is 4 co-circular points. And everything is rectangles. It better work. And of course, a square grid of points is one of the cases that we were doing very early on to get the algorithm running. Here's an example of a polygon, that little triangle with antennas there, and segments and points all being run through the algorithm. And so we can see, if you make a graph, you can tell by walking from this point outward in a kind of a breadth first search what he's near to do nearest neighbor type queries and that sort of thing. Here's another example of degeneracy. This time is co-circular line segments where we have the higher order Voronoi vertex in the center.
Can you back up one?
Sure. So for example, this is the medial axis of the triangle.
One section on the upper left, well, the one beside the one with the dot in it. That one right here, yeah. What's inside of that?
This point.
Just that point?
Yeah, this is the cell equidistant to that point. Because the point is modeled separate from the segment body. So this is an edge between the endpoint of the segment and its body. And so that's dividing what's equidistant from the body and its endpoint. And if we wanted to consider them the same, you just dissolve this away, and this whole thing becomes the cell for this segment and its endpoints. We need those, especially for the medial axis, you can see. If it was not a convex polygon, it would be more clear why we need them. Here's Voronoi diagram for the letters boost, several polygons and groups of line segments there. Now our benchmark results have been keeping you in suspense. We ran, logarithmic progression of point clouds through the student's algorithm implementation in Seagal. And of course, Seagal should be exactly correct 100% of the time, whereas we have our relative error correct result. So I'm sure the Seagull people would not be happy with such a direct comparison. But we see that at 1,000,000, which is the point where I even start caring, we're 22x faster, and it's something about 12 seconds. And the other thing to notice about this is the exponents, and you can't actually see them because of the resolution. This is 1.07, which is n log n, empirical time complexity. This is 1.3, which is somewhere between n log n and n to the 1.5. But if you look at it, these 2 points are below the line. These points on the end are above. So it's actually curving on the log plot, which tells us that there's a little exponential factor sneaking in there somehow, which could actually be the way they handle the numerical data type. So classic Achilles heel of the sort of lazy exact numerical data type that they may be using in Seagull. So with the new algorithm, we have the potential for a bunch of new APIs to be added to Boost Polygon. Where here I'm proposing an interface for getting the Voronoi diagram of an iterator range over points, where the output type is some container that can accept polygons, which would be the cells as polygons. And then the Delaunay triangulation of points the exact same way, except now the container is triangles as polygons. And the Voronoi diagram of a polygon set, the output type is your cells again as polygons, where the edges of the polygon would be your line segment sites. And we have this distance threshold, which is an instruction of how to segment the parabolic arcs so that the distance between the segmented arc and the original arc is bounded by this threshold. So it gives you control on the error on how you segment that when you represent it as a polygon. Most algorithms can't really consume the parabolic arcs in the Voronoi diagram of line segments, but the approximation as a segmented arc is acceptable.
Sorry, I just wanted to ask, did you, maybe I missed it, were you able to do on those, on your benchmark results, were you able to see to what extent, if any, the topologies differed from those that Seagull produced?
He did those just this week, and I actually got them yesterday. So I haven't had a round-trip communication really with him. I don't know of any comparison made on the output. I should probably mention testing at this point. He's been pseudo-exhaustively testing it with randomized test data, and we have a number of sanity checks on the output, so we can automate the validation of the output, because if you have large point clouds and a Voronoi diagram, how do you know it's wrong? So we test, is it planar, which is basically do any of the Voronoi edges cross, which would be an incorrect topology for sure. Of course, you could have an incorrect topology that's not detected by that. There's other sanity checks as well, are there two sites within a cell, and so on and so forth. And that's one type of testing, and then we also create the hard cases and go through those and validate them by hand.
But you don't know how much the topologies would differ?
So, by our error bound on the circle event, right, we could get them out of order, but the distance between them would be very, very, very small. And so
it might be a different topology, but it's virtually equivalent.
Yes, say you had 4 nearly co-circular things. You might end up cutting it one way versus the other, and it's still planar. Is near correct to below your ability to even detect that with normal floating point comparisons. And it's hard to imagine that would be a fatal error for the consumer of it, since they're so nearly equal that it's hard to tell. Is probably acceptable. But that comes back to reasonable. right? When you're making the approximation, what's safe? Okay, it was safe. Is it reasonable? Probably. It depends on the application. If you're Seagal and you get a different result, then you can say, no, it's not reasonable, it's wrong.
Right.
Technically it's wrong, but
So you haven't done, part of your test suite isn't comparing the Seagal. and seeing
Not
how
currently.
often-
he only just got it up and running. And part of that is intentional, because we don't want code contamination. They have a very ugly license. And I don't know who they would sue. Maybe we just don't want the code contamination. We don't even want to know what their interfaces look like to use it. We don't want to use the same names because there's automated tools that check for that sort of thing. No, seriously.
No, I know.
They made me run them before they let me release Polygon. Before I could show it, there was like a year I was talking about it on the list. I couldn't show it to anybody because I didn't get permission. It took so long. So for the Google Summer of Code 2011 project, my idea is to do line segment based concepts. So the input line segments to the Voronoi diagram of line segments need to be non-intersecting. So that's a precondition of the algorithm. And it's a postcondition of the line segment intersection algorithm I implemented for boost polygon to do the Boolean operations on polygons. So that it'll fit together nicely. But to really make good interfaces for the Voronoi diagram of line segments, we really need line segment concepts in the library so that we can make generic interfaces to interact with the algorithm. So what I'd like to do is have a line segment, directed line segment, set of line segments, and set of directed line segments all implemented as new generic concepts and have a generic API around those to augment the existing geometric concepts in the library. So a directed line segment is a refinement of line segment. A set of directed line segments is a refinement of set of line segments. And directed line segment would be a refinement of set of directed line segments, which restricts it to only one. And polygon is a refinement of set of directed line segments, if you view it that way, you know, with your winding rule. And any algorithm interface that expects a set of line segments would accept a rectangle then, because a rectangle is a refinement of a polygon, is a refinement of the set of directed line segments, is just a refinement of a set of line segments. And then all of these geometric data types become compatible with the new concept-based APIs. And in a very similar way to the way all of the polygons and points and rectangles that are currently concepts in the library work. So, as a result of the Google Summer of Code project this year, which isn't really getting off to a good start, I'm a little concerned. I'm also kind of spoiled with how well last year went. I hope to add these types of interfaces to the library, where we have container types of edges to to store the Voronoi diagram, or have inputs of edges for computing Voronoi diagrams. As well as to compute the medial axis of a polygon set, you probably want that as the edges. So that's the API I'm proposing for that. And so I'm always taking the output by reference on the container type, just to be consistent with the way the API currently works. That's my personal style for pushing responsibility for that object onto the caller. Well, that's it. If you have any more questions, my throat isn't completely dry yet, so we might be able to get them answered.
So did you, I don't really know if this is a good idea. What about using fixed point instead of floating point?
Well, if you think about it, the integer coordinates at the input and output essentially are fixed point. And fixed point doesn't really buy you much. You know, it's basically why not use infinite precision integer calculations? Because you keep making larger and larger fixed point representations to store the result of multiplication and stuff.
Well, I think actually not, right? I mean, the fixed point, you would specify a certain level of precision that you're going to get, and you're basically going to get your error at that level.
Well, you can still have cancellation error with fixed point, and you still have rounding error, and so you have all of the exact same problems as with floating point. As well as it's more work to use it and it's slower, because you kind of have to emulate the behavior of the multiplication and stuff.
I'm not sure you get all the same. The rounding error and so forth is different, right? I mean, it's...
Well, you would have a policy, probably, depending on how you implement it. But in floating point, we know it rounds to the closest in the last bit, except for square root, where they have a little asterisk that they say, we'll give you a error that's twice that, basically one full ULP at the worst, because it would take a whole nother iteration of our expansion of the square root to get you that last bit, and we know you don't care, so it's 1 instead of 1/2.
Well, I mean, I realize we don't necessarily have, and it's possible I missed something, but I don't think we have an implementation of fixed point laying around.
Oh, yeah, that too.
But
there's an idea kicking around for that, and
well, there's actually a proposal for the standards committee that's been put forward by IBM for a TR that would actually add it.
That would be nice.
And then you would actually, I think the whole idea was that we would at some point actually get hardware support for it, which would of course then make it flat fast. But,
well, we have integer support now. Let's see.
But yeah, I don't know. It might be. I mean, obviously, like I say, you have some different properties with respect to the error. I don't know if it would ultimately be better or not.
Yeah, the way I like to do integer computation is to just double the size of the representation when I multiply, and then I add, and that's how I get to 65 bits. And I emulate that with an unsigned 64-bit and a bool. And you can do that with GMP infinite precision integer up to however big you want, and including square roots to however big you want, but you have to tell it when to stop. And that's an option for how to do it. And if you choose integer input coordinates, it's an option that's open to you. Whereas if you choose floating point coordinates, then you can't really go with infinite precision integer as your strategy for dealing with numerical robustness. What we're currently doing, infinite precision floating points is some ways a little easier to deal with.
I was just wondering, because I haven't done this problem before, where you have the polygons in your Voronoi diagram have if it's a Voronoi diagram of edges, right? You have parabolic. Some of your edges are parabolic. Yeah. I was wondering what that does to like some of your algorithms, like point inside polygon, and how do you make use of this? That must be a lot harder.
So if you have a point, since you mentioned that, let's go back to this one, right? So let's say we're asking, is this point inside the polygon? You would probably not segment the arc. You would just have it be an edge with a node in the graph, and it says, oh, this is the outside edge of the polygon, and I'm on the other side of the Voronoi edge from it, so I must be outside. If you segmented it and viewed it as a polygon, and then you ask, is the point inside? We would hope it was, even if it had been segmented. If this, for some reason, was really squashed, then it could become arbitrarily close to the point, as these two line segments get arbitrarily close to the point.
Well, I wasn't really thinking about your site, so I was thinking more like an arbitrary point.
Oh, an arbitrary point.
Like, it must be hard to do.
Well, in order to reconcile the arbitrary point with the graph, you would either have to walk the whole graph or put it in a query tree, which which
Okay.
doesn't make sense. Normally, you would put the point into the input of the problem itself. But I suppose if you already had a cell and you just wanted to ask, is it inside or outside, and you had segmented it, you could at least look at the edge it was close to and ask if it was within your threshold that you specified on the segmentation of the arc.
I guess the answer is this problem isn't normally applied to the issue of an arbitrary random other point. Like it's normally every point you care about is actually in the problem.
Yeah,
Okay.
that's how you do it. And, you know, you could do, it actually solves some of the same problems that you can solve with my library currently. Like, I build the connectivity graph of and mutually overlapping polygons. And if you ran them through line segment intersection and then did the Voronoi diagram and walked the graph, you could reconstruct the exact same information. And then it just becomes a question of which is more efficient, I guess. It's very flexible what you can do with it.
So you, go ahead.
I was just going to say, where can we download this? I mean, that was on the slide I missed.
It's in the sandbox. The tests compiled and worked last time I ran them. There's a cute visualizer which makes this for you, and it's pretty speedy in terms of running 1,000,000 points in 10 seconds. It's competitively fast with the Boolean's algorithm in Polygon. It's roughly the same speed to do a Boolean operation of the same size for vertices of polygons. So I'm pretty happy with the quality of it, both in terms of how much testing we've given it and how fast it is. The points is probably in better shape than the segments now. It's been working longer and gotten more testing, basically.
So you were saying that it's not going as well this summer code or something, or you were...
Yeah, do you want to open that up?
Is it a different student?
Is a different student.
Okay.
I wish I had the same student. He actually offered, if it doesn't work out, I'll just do it. I don't even have to get paid by Google, just because he wants the nice interface for his
Did he not reapply? Because you can do it twice.
He didn't reapply, and it was too late, and I didn't have other good applicants. And, what he's already done and what he was paid for, I don't think he really cares that much about the money.
Apparently.
This could turn into a PhD dissertation for him eventually.
Is he actually at the university now? Or what?
He's a master's student in the Ukraine, majoring in applied math. So this is applied math.
Yeah.
This is
Yeah.
This is definitely his field.